Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture on this topic of control systems, which we've started discussing a few lectures back, that is state space methods. So in the preceding lecture we introduced this so called matrix exponential, and we also showed you that this is not really an exponential in the conventional sense of the term, that is the exponential function that you are familiar with, which exists nonetheless. Here we notice that this particular object that we encountered, so the object that we encountered whilst trying to solve this state space equation was something like the Laplace inverse of Si minus A inverse, right, and we found that this has a series expansion which reminds us of the exponential series, and therefore by analogy we just called it e to the at. So remember, I said it the last class as well and I will repeat it, this is by definition, okay, so there is no question of deriving the expression for the matrix exponential, okay. The matrix exponential by definition, in view of its analogy with the exponential function, is called so. It is an infinite series which provides us a solution, basically to be more precise the zero input solution of the differential equation or of the state equation is given by by evaluating this matrix exponential, okay. So of course I said that you can expand this in the same conventional way as we generally expand out this binomial series, right, or rather the geometric series for that matter, yeah, and you might be a little uncomfortable. Well, there is one way to check that this Si minus A inverse, which we cleverly sort of wrote in this form, right, this plus A by S plus A squared by S squared plus so on and so forth, yeah, this infinite series ad infinitum, yeah, this is indeed this Si minus A inverse. How to check that? Well, you just multiply both sides by Si minus A, whether on the left or right, it does not matter in this case, and you see what this is. So on the left hand side you have identity, of course, and what about on the right hand side? So if you just multiply this by Si minus A times 1 by S times this series, yeah, you just take a first few terms, the sample terms, and you will see that this is what happens. So you basically have I minus A by S times I plus A by S plus A squared by S squared plus dot 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 till infinity, yeah, an infinite series. So now you open this up, so of course by multiplication with this identity you will just get back I plus A by S plus A squared by S squared plus A cubed by S cubed dot dot dot. That is one part, yeah, and the other part of the sum, of course there are still technicalities involved here, but this is just a quick sort of a way to convince yourself that we are not just building castles in the air. Then you will have A squared by S squared minus A cubed by S cubed, likewise so on. So you see every other term, yeah, every term other than the identity vanishes. So on the right hand side also you have I, so it is basically identically true. So that is one way of convincing yourself that the series expansion that we carried out in the previous lecture is actually valid, okay. So in today's lecture we are going to try and look at a few more different methods of Actually not in today's lecture, we are trying to initiate that discussion, probably we will see that in a succeeding lecture. But in today's lecture we are going to sort of lay the foundations for certain tools, yeah, we are going to introduce certain tools which will then let us evaluate this e to the at, yeah, without having to go through this trouble of doing this Laplace transform and its inverse and all that, right. See, the thing is, we had this transfer function based approach towards solving this ODE, yeah, where we found that, well, it was self contained, but now we have come to this state variable method and we see that, you know, eventually if you want to solve the state space equation, you will finally need to resort to this Laplace inverse. So you may not be very happy with it, you might say, well, after all you have introduced this new paradigm, so can't we have something independent of the existing methods, like independent of this Laplace inverse and Laplace transform business? Isn't there a more elegant way or a more straightforward way that is independent, so that someone studying state space methods might as well choose not to adopt those inverse Laplace transforms, etc., and still be able to solve for the state space equation. Another important point there is, now notice that we said that this solution of the state space equation, we said this xt was given by this a t x naught, where of course we are assuming that x at time t is equal to 0 is x naught, yeah, and then we saw that this plus, then we have this convolution integral, yeah, where a to the a t minus tau. So I am writing it formally here, b u tau d tau. Earlier I had just written this as e to the at convolved with but, yeah, that is what this term is, right. So maybe let me color that with a different ink, yeah. So this is what this term is, this is this convolution integral, now I am writing it down this way. Now you might say, well, hang on, this is not the entire solution of the system, right, because after all we want the output and you are giving me the state. The state is something that you cooked up, right, the state wasn't there in and of itself. You had a system where there was an input and there was an output, the input was u, the output was y, but now you are just giving me the state which is something that is probably a figment of your imagination, yeah, maybe you have built some op-amp circuits, I do not know, but nonetheless this is still something that you have constructed, but I am not interested in this, I am interested in the output. So what good is this? Well, it just takes a while to notice that once you have x, after all what is y? Y is nothing but c times x, right. So whatever you have as x here, you just apply a pre-multiplication by c and you see that the moment you have solved for x, you have also solved for the output as well. So in that sense this is the complete solution, right. So this actually should motivate us to take a very close look at this e to the at, right, because not only is this involved in this so called zero input response, but it is also related to this zero state response, yeah. You see inside the integration you have this e to the at sitting comfortably, of course because of the convolution it is shifted like this, yeah, but the key to finding all of this, whether you want to find the zero input or the zero state or the complete solution of this, yeah, is in being able to evaluate this e to the at, okay. So we will keep this question burning in our minds, we will realize that this is what we are essentially trying to get a handle on. We already have seen one method, it is not as if we cannot do this, yeah, with the knowledge that we have we can already evaluate e to the at by this e to the at by this Laplace inverse. So we take this, you know, this a's are constants, yeah, a is a constant matrix, so this s is all that you need. So therefore all we need to do is this e to the at, we need to take this this big matrix A, operate it with Si minus A and take its inverse, and then take the Laplace inverse of every single entry of that resultant matrix, yeah, and we will be done. But again this is easier said than done, as you might have noticed in one of the earlier lectures where we try to do an inversion of a 3 by 3 matrix and it takes a bit of careful calculation, etc. So it is not a very pleasant thing to do. Of course I am not saying that the methods we are going to propose is going to be way simpler than this inversion, but at least you will see that they turn out to be of a different flavor at least, right, apart from the fact that you do not need to use this Laplace inverse. So anyway, we will probably do that in a later lecture, but in today's lecture, keeping this question burning in our mind, we will actually take a kind of apparent digression, although later on by the end of this lecture you will see that what we will be doing is very intricately and intrinsically linked with this our quest for a method to evaluate e to the at. So we will only discuss maybe 2 methods or so. There are several other methods in advanced level textbooks on controls, graduate level books, you can look them up. We will only discuss 2 such methods apart from this Laplace transform based method that we have already introduced, right. So bearing all this in mind, we will now take the slight digression into something called similarity transformation, similarity transformation. So you might wonder, what is this similarity transformation business? You understand from high school knowledge of geometry that there are things called similar triangles, right. So there can be like triangles which can be scaled up and down to a certain size, but basically their angles are the same. That is similarity between triangles. So what is similar between this similarity transformation and what is it actually transforming at the end of the day, right. So I would like you to look at this as some sort of a substitution, or a, in more technical terms, linear algebraic terms, it is basically a change of basis. So to give you a quick example, suppose you have this x and y coordinates like this, alright, and you have a point here. So you denote this point by AB, so this is like a vector on this 2-dimensional space, yeah, and by AB it is unambiguously understood that this means that A has basically an x component that is A, sorry, this point P has an x component that is A and a y component that is B. In other words, if you take a vector along the x direction of length A and you take another vector along the y direction of length B and you take their vector sum, so you know the parallelogram law of vector addition, then this is the vector that you get, yeah. So that is basically what this coordinate system is. Now suppose I am not particularly keen on choosing this particular xy, suppose I am not very keen on this 90-degree thing, so I choose my 2 vectors like this. Let me use a different color. So suppose I choose my vector to be this as my v1 and this as my v2, yeah. So it is a result in linear algebra that says that in a 2-dimensional space, or rather in an n-dimensional space, you will need exactly n linearly independent vectors to represent any other vector. That is called, that set of n linearly independent vectors in an n-dimensional space is called the basis. It turns out the most natural basis that we choose in Euclidean spaces are the x axis, y axis, z axis, and you know, if you higher dimensional, then those orthogonal set of axes that we have already got naturally occurring, right. So that is why we have the standard set like 1 0 0 0 0, that is one, then 0 1 0 0 0, that is another, right, likewise till we get 0 0 0 0 1, right. So if you take this as a set of vectors in n-dimensional space, then you take any vector, say alpha 1, alpha 2 dot 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 till alpha n, it is basically nothing but alpha times this 1 0 0 0 plus, sorry, alpha 1 times this, alpha 2 times this 0 1 0 0 0, right, so on and so forth. So it is very conveniently represented in terms of these fellows that I have chosen. So this is basically what is called the basis, right. Now it turns out that I can always change this basis and I do not have to choose them to be orthogonal or separated by 90 degrees. You can understand what orthogonality between these fellows mean by a simple dot product. You take the dot product of any 2 of these and it turns out to be 0, right. Just like from geometry itself you can see here the x and y axis are orthogonal. So that is the notion of orthogonality. Again, without getting into the nitty-gritties of linear algebra and such topics, you can understand this intuitively at least. And for now, for this particular subject, after all it is an undergrad controls course, this much understanding should suffice. So what I am saying is, now instead of this erstwhile x and y that I had here, yeah, I am now choosing this v1 and v2 as my new basis, yeah. So then that same point P here, yeah, which was given by a comma b earlier, that means this was of length a, yeah, and this was of length b. So now I want to represent this in terms of V1 and V2. How do I do that? So geometrically the construction would look something like this. So I have to basically think of some alpha times V1 plus some beta times V2, which gives me this point P. What does that mean? That essentially means that I have to take alpha times V1, beta times V2 and take their vector sum. So I have to apply the parallelogram law, right? So in order to do this, what I do is I take a line parallel to V1 passing through P, okay, and I see where it intersects V2, and then I take a line parallel to V2 passing through P and look where it intersects V1, and that way I would have completed a parallelogram, yeah. So then this is my same resultant P now. So this basically, if this is my direction of V1, this is my V1, then this is alpha times V1 and this is beta times V2. So if I compare the length of this segment, this smaller segment with the overall segment, I get alpha. In this case alpha is less than 1, as is beta, right. So in this case the length of this small segment compared to the overall length of beta of V2 gives me beta, right. So in this case both alpha and beta happen to be less than unity. It is not necessary, it could be anything. So in this case this is how you can geometrically in 2 dimensions see what alpha and beta are like, right. So then in terms of this new basis, this V1 and V2, now it is no longer AB but it is alpha comma beta. So P can now be represented as alpha comma beta. Earlier in this old basis this P was A comma B. So it is a new representation of the same vector. Now of course you can immediately see that when you go to higher dimensional spaces, I cannot do this geometric construction, yeah, and show you very transparently what it's like, but there you have to take a sort of a, you have to let your imagination run a bit and then see that, and that's why we do abstract linear algebra in fact. So if you just extend your imagination a bit, then you will notice that basically if higher dimensional spaces we can carry on doing the same thing. Instead of choosing the standard basis that we have here, we can choose any set of V1, V2 dot 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 till Vn as another basis which is a linearly independent set, right. So that is what gives rise to something called a similarity transformation. So if you've understood till this point, we'll put a stop to our discussions on linear algebraic perspectives at this point and we'll now get back to the control theoretic aspects. But later on when we are done with this similarity transformation with respect to the state space equations, I hope that you will be able to at least relate to this discussion that we've had on this, yeah, and be able to see the connection between the two, okay. You can take that as an exercise, revisit this and try to find the connection after we are through with this similarity transformation on state space systems, okay. So what is this similarity transformation? So apart from the fact that this similarity transformation allows us or will allow us to obtain a method or a process to evaluate this e to the at matrix, this matrix exponential, there is also another question or another sort of claim that this similarity transformation will justify. You recall that a while back, maybe towards the introductory part of the state space methods, I had drawn a figure like this where we had said you have this ODE and you have this transfer function, okay, and from this ODE to this transfer function it goes both ways. You can have a state space realization 1, you can have a state space realization 2, likewise you can have a multitude of state space realizations, yeah, you can have state space. So it turns out you can have an infinite number of state space realizations, that is what I had claimed, okay. So now at least one thing is there, that whether there is a connection between these two is actually a difficult question to answer at this point, yeah, with the kind of knowledge and sophistication that we have at the moment. This question is best left unanswered at this juncture, yeah, whether you can go from any state space realization of a given transfer function or ODE to another, yeah, that is a question we shall not probably deal with in this course, okay. These things are fairly routine in an advanced level controls course such as multivariable controls or any advanced graduate level controls course for that matter, but in this course we will probably not have the scope or the opportunity to address that question. Nonetheless, I can partially address some of this question and at least convince you that there does exist an infinite number of state space realizations from the ODE to the transfer function, and that is very liberating, because remember initially we started with this premise that the output of every integrator has to be chosen as a state. Yeah, then we relaxed it a bit and we showed you at least 3 different realizations. We showed the phase variable canonical realization, we showed the diagonal or the Jordan block sort of realization in the block diagram form. Yeah, so we showed at least 3 realizations after starting with that first one. Yeah, so those have names, we will get to those names once we are familiar with terms such as controllability and observability, don't worry about them. We will not introduce any more of those forms. In standard graduate level textbooks you will find some more canonical forms of state space realization. We will not go beyond the 3 forms I have already introduced in this course. So that is where I draw the line. But now in view of the similarity transformation, one thing that I am going to address is I may not know whether there is a connection between these and these, there is a way of going from here to here. Now here to here I know that this C Si minus A inverse B, yeah, so that allows me to go in this direction, right, and of course from this ODE I know this ODE to this I have this 3 methods we have learned at least. There are several other methods as I said, but we will not get into that. At least we have learned 3 methods: the phase variable canonical form, the diagonal realization, yeah, when we had that we also covered the special cases of diagonal cases where we had the repeated real poles or complex poles, even those cases we considered. So at least you should be able to now go from any ODE to its state space realization, that we have seen. This, as I said, this dotted line part we will not consider. Let us see, if we have time we might, but no promises on that. However, what we are now going to show you is that once you have generated one state space realization, then you can generate from that state space realization an infinite number of state space realizations. Yeah, so these themselves in themselves will be uncountably infinite. So every one of these state space realizations that you might have generated from the original ODE will in turn allow you to generate an infinite number, an uncountably infinite number of state space realization. What's more, and this is the crucial bit, at this level we had this dotted line here, the peer level, right, we didn't know if we can go from 1 to 1, but within this set that I have drawn around this, or maybe this set that I have drawn around this, or maybe this set that I have drawn around this, you can go between any 2 of them. Yeah, tall claims there, right, I am making, and this is what we are going to see in today's lecture primarily. Yeah, that not only does every state space realization that you get from an ODE or a transfer function yield an uncountably infinite number of state space realizations therefrom, but also they are all like it's an all-to-all connection. Yeah, so you can go from any state space realization to any other through this so-called magical tool that we shall see today called similarity transformation. So even if these connections are a bit hard to make, whether they are actually you can go from one to the other here, but at least within this black contour here or within this blue one or this red one here, among these at least you can go within this, right. So every one of them you can travel from one to the other through similarity transformation. So I have said quite a lot and it must have now piqued your curiosity quite a bit that okay, a lot of things have been said about this similarity transformation without actually mentioning what this is all about. You might be growing a little impatient at this point. So let me get to that. What is a similarity transformation? Remember, we have already planted the seeds in your mind in the sense that we have told you that similarity transformation in a linear algebraic perspective is basically nothing but like a substitution or a change of basis. Routinely you have been doing these substitutions. Yeah, I remember when you did integrations in your +2 level courses, maths courses, right? You often changed variables. Yeah, you substituted one variable for the other to get it into an integrable form, in closed form, right? So it's some sort of substitution in that sense. How do I say that? Now suppose you have this bunch of vectors x1, x2 dot 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 till xn. This is this vector that belongs to this r to the n, right? And now this r to the n, if you for example now transform this, say from here you go to some say summation alpha ij or alpha 1j xj, j going from 1 to n, then summation alpha 2j xj, j going from 1 to n. Likewise, then you have summation alpha nj xj, j going from 1 through n, yeah, and where these alpha ij are real numbers. Okay. So, suppose once you have been given a set of n states, which basically, remember what are states, they capture the memory of the system, right. So, there is actually an engineering sense, common sense, the reason why we chose the output of those integrators as states are because the integrators are basically the memories of the system, right. Whatever has happened to the system up until the point when I begin my observation, which is t0, yeah, is captured by these states. So, I do not need to worry about what has happened in the past, so long as I have information about these states at that instant t0, that is what defines a state, right. So, the point that I am making now is that given that I have these states and I take this sort of what I call a linear combination of these states, yeah, and I cook up n such linear combinations, but such that none of them is linearly dependent on the other. So, what can this be written as? You see, this is basically nothing but alpha 1 1, alpha 1 2 like this, alpha 1 n, yeah, alpha 2 1, alpha 2 2 dot 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 till alpha 2 n, so on till alpha n 1, alpha n 2 dot 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 till alpha n n, yeah, and this is basically x1 x2 dot 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 till xn. So, what I am saying I am doing here is I am basically taking this x and let us say pre-multiplying it by this some matrix T, okay. But instead of calling it T, I do something funny here, I actually call it T inverse. What am I doing by that? By that I am also adding this condition that this matrix whatever I am cooking up is invertible, okay. So, you cannot just take any arbitrary linear combinations like this, also whatever linear combinations you take and as a result if you write it down like this, then this resultant matrix will be invertible. So, what I say is that from x, yeah, I operate with a T inverse and I get to a new set of states which I call x tilde, okay. So, this is the transformation that people choose, okay. Why is this a similarity transformation? What is similar about it? We will get to that in a while, but for now you please notice certain key important observations here, alright. So, what are those observations? Let us go to the next slide here, yeah. So, notice that you have this x dot is equal to ax plus bu and y is equal to cx plus du is the standard notation, right, yeah, okay. And now let us say I define this, I call this matrix T inverse instead of T. So, why am I calling it T inverse? Because then in one shot it is as if I am saying that not only is this a matrix which transforms x to a new variable x tilde, this vector x into a new set of vectors x tilde, but also this transformation matrix that is capturing this transformation is invertible. What do I mean by invertible? So, again this will require a little bit of understanding of linear algebra, but not much. I hope that you have done such a course in on linear algebra at some level or matrix theory at your undergrad level, right. So, remember this x belongs to R n cross 1, A belongs to R n cross n, B belongs to, because it is a seesaw system, R n cross 1, C belongs to R 1 cross n, and D is obviously a scalar, right. So, now what does it mean to say that this T inverse exists? There are equivalent conditions for this. So, one is it says that T is non-singular, which is tantamount to saying that the determinant of this T, remember this T that I have defined here, this T is also a square matrix, no, T and T inverse, they are both square matrices having the same size as the A matrix, right. So, therefore, A and T are compatible for multiplication as they say, right. So, the equivalent condition for T to be non-singular is that determinant T is not equal to 0, and there is also another way of seeing this, that is to say that T times V is equal to 0, yeah, that is to say that if t times v is equal to 0, then v must be equal to 0. In other words, if you take the columns of this T matrix, so this is one column of T matrix, column 1, this is column 2, this is the nth column, yeah. So if you take these columns of this matrix, these are all n tuples, these are all vectors in Euclidean space, n dimensional Euclidean space. So if you take these columns and if you take the linear combination, when you are taking this T times V, that is what you are doing, yeah. Just see, if you take this, if you call this T as say T1, T2 like this till Tn, these are basically all columns of T, yeah, and if you multiply it by V1, V2 like this, so this is the V vector, yeah, this V also belongs to this n tuple, yeah. So then that is basically nothing but V1 T1 plus V2 T2 plus dot 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 till Vn Tn. So when you are saying that Tv is equal to 0, you are basically saying that this whole fellow must be equal to 0. And if this fellow is 0, then we are saying that the only way that can happen is if it is trivially true, that is all the V's are 0. If any one of the V's is non-zero, then there is no way that these fellows, their linear combination, this is what the linear combination is, then their linear combination cannot go to 0. That is the condition for linear independence of the columns of the matrix T, which is also the condition for basically T is of full rank. So I am sure that at some point in your courses you have heard of this rank of a matrix, right. So column rank, row rank, it's the same thing, yeah, the column rank and the row rank of a matrix are equal. So especially for a square matrix, it's a no-brainer really. So what we are saying is that this T better be non-singular, which is why we define this transformation instead of by T, we are calling it a T inverse directly. So that assumption that T is invertible is already embedded in this, right. So in going from x, given that I have a set of x given as my state variables, if I want to choose another set of states, the only thing that I need to look for is a non-singular invertible matrix, yeah, non-singular and invertible are same. So all I need to do is look for n cross n invertible matrices. As soon as I have found it, I have another set of states, yeah. So it's that simple, it's very liberating, because now as I said, you don't have to look for these outputs of op amps and the integrators and think that those are the only ways you can define your states. Of course from an engineering perspective that makes a lot of sense, but as a mathematical analytical tool, you can choose a plethora of state space representations now, right. So at least I hope that I have given you this part, not quite though, so that picture still remains. Now I have given you the original system here, that picture still remains to be explored. Now what if I pass this like x tilde is equal to T inverse x. So let us see what is x tilde dot, that is going to be T inverse x dot, yeah. So if it is T inverse x dot, then this is going to be nothing but T inverse Ax plus Bu, I am substituting from here, yeah, nothing else, right, just that. So that is going to be T inverse Ax plus T inverse Bu. But remember I have this x tilde on the left hand side and on the right hand side I have x, so why not plug in this, yeah, represent this x in terms of x tilde. So what I then do is T inverse A, and this x I already know what this is, right. So from this relation I know that x is equal to T x tilde. So better replace this x with T x tilde plus T inverse Bu, yeah. So therefore what I then have is, if I now want to compare this A tilde x plus B tilde U, then I have that this B tilde is nothing but this T inverse times B, and this A tilde is nothing but this T inverse AT, yeah. What about the output equation? So let me explore that. Output is y is equal to Cx plus du, yeah. So now that is going to be C, what is x in terms of x tilde, yeah, just notice this. So if I replace x with variables in terms of x tilde, as I said, it is just a substitution, yeah. So this is T x tilde, of course nothing changes here, so this is du. So then I have this is equal to C tilde x tilde plus D tilde U. So then I have that C tilde is equal to Ct, D tilde is equal to D, A tilde is equal to T inverse At, and B tilde is equal to T inverse B. Yeah. So I can easily write the two systems x dot is equal to Ax plus Bu, y is equal to Cx plus du, and x tilde dot is equal to A tilde x tilde plus B tilde u, y is equal to C tilde x tilde plus D tilde u, right. Now you might wonder at this point, what is this business that is happening, why are we suddenly interested in this, what is so special about these two systems, are they in some sense equivalent, is there any connection between these two? I understand that I am transforming the states from one to the other, but if you are claiming that you can generate all of this, can we also go back following along this route and trace it back to the same ODE or transfer function? It should be doable, right? Because you see, now I have shown you that this, it's possible. So let me just tick off the connection that I have shown. I have shown you that it's possible to go from here to here. Just take T inverse At. If this is A, B, C, D, yeah, the 4 matrix is A, B, C, D, then you take T inverse At, T inverse B, yeah, C, T and D, and you get here. If you want to get from here to here, that is also not very difficult. You just take the same opposite transformation, no. So you take, for example, this, you want to go from A to A tilde, A tilde to A, then you have A is given by T, A tilde, T inverse, B is given by T, B tilde, C is given by C tilde, T inverse, and D is given by D tilde, yeah. So I can go back and forth because of the invertibility of this T matrix, I can go back and forth, alright. So at least this connection in this figure, this connection I have established, okay. There is no doubt about this connection now at least. The connection that I have not yet established is that I can go from this to this. So what am I going to do there? Suppose I have this system and using the matrix T1 I have gotten from this to this, but using the matrix T2 I have gotten from the transformation matrix T2, I get from, let us say, x hat dot is equal to A hat x hat plus B hat u, y is equal to C hat x hat plus D hat u. In other words, what I am saying is that basically A hat is equal to T inverse At, B hat is equal to T inverse, so T2 inverse, sorry, T2 inverse B, C hat is equal to C T2, and D hat is equal to D. Just like here, now I can replace this with T1, yeah, sorry, not that one. So let me call this just 1, I am just, because I am lazy, I do not want to rewrite this again, yeah. So this is the T1 transformation. So this relation, this here, and this is this relation, right. Now I want to establish the connection between these two. If I am able to do that, then I would have established a connection between these peer groups, yeah, and then by extension a connection, a similarity transformation exists between all of them. I mean, this is sort of a similar operation that we are carrying out, right, this taking an invertible matrix and transforming. So if there exists some invertible matrix which takes me from one state space realization to another, sitting within this one sac, this black sac here, yeah, then that exists between every one of them, right. So let us at least try and establish that bit of the picture. So how do we do that? It is very simple. So you have this x, just the connecting link there between them is this x. Notice that what is this x we have defined here? We have defined this x tilde, so let me go back and correct it and make all of this T1 instead of T, yeah, to make it consistent with what we have defined it later, yeah. So this is just T1, I am just changing all the T's to T1 because later on I have introduced T2. So what we have is this x is equal to Tx tilde. So Tx tilde is equal to x, but that is also equal to T2 x hat, yeah. So basically x is the connection between them. So then if I now remove this x, what I get is T1 x tilde is equal to T2 x hat. Now because both T1 and T2 are invertible, I can certainly write x tilde as T1 inverse T2 x hat, or it is a matter of taste. If I want to write x hat in terms of x tilde, then I will write T2 inverse T1 x tilde, yeah. So suppose now I call this my new transformation matrix T. So then I have the same sort of similarity transformation between x tilde and x hat, isn't it? Yeah, or if I want to call this, let us say x hat, I want to call this T bar, then x hat is equal to T bar x tilde. In fact, you will see that T bar is equal to identity. Yeah, it is pretty obvious, no? So therefore, from this you see that the claim that I had earlier made right at the beginning of this class today, that once you get one state space realization, and if you generate more state space realizations through the similarity transformation, then each of those realizations, new realizations, you can go from one to the other through a similarity transformation. That is all I have said. I have never even, not even advertised this similarity transformation sufficiently yet, yeah. I have just told you that you can get to the similarity transformation. But again, I need to establish the motivation behind the similarity transformation. What is so good about the similarity transformation? Does it preserve something? Like similar triangles, they preserve apparently the angles, right? Yeah. So what is invariant? So the question that we ask is this one of invariance, yeah. Invariance under similarity transformation. So that is the vital question that we want to answer now. What is so invariant under this similarity transformation? So towards that, along that direction, let us try to take a look at this another notion. Again, it will look like a bit of a digression, but I assure you it is not. So this notion called poles and eigenvalues. Poles you already understand, right? You know that if you are given a transfer function, yeah, you know that the denominator polynomial, rational transfer function, ratio of two polynomials, then the roots of the denominator polynomial turn out to be the poles. And now we have seen that this relation between this transfer function and the corresponding state space realization is given by this. Now what is this inverse, I wonder, right? We already know that this is given by the adjugate of Si minus A. The adjugate of any matrix is the transpose matrix of its cofactors, yeah. So then by determinant of Si minus A, yeah. So this entire thing then turns out to be C times adjugate of Si minus A times B, and if you have the feed forward term, then of course also this D makes an appearance. D is nothing but a scalar in our case because we are dealing with seesaw systems, right. Now if that is the case, then what can we deduce about this? Notice that this is after all the GS, right. So GS normally we are used to writing in this fashion, NS over DS. Now by comparison with this, we see that this DS is nothing but this determinant of Si minus A, which again has a name. This is called the so-called characteristic polynomial of A, okay. We call it, let us say, chi A of S, okay. So we call this a characteristic polynomial, this determinant Si minus A, alright. Now there is an observation that I would like to make at this point. So often in control theory and in undergraduate level courses, we interchangeably use terms like poles and eigenvalues. Now there is a reason why, because it turns out that by solving for this roots of the characteristic polynomial, yeah, solution gives us the eigenvalues. In the next lecture or so, when we discuss more methods on evaluating e to the at, this will become clearer. So if you want to evaluate the eigenvalues of a matrix A, it turns out that you need to solve for the roots of the characteristic polynomial, yeah. So these are the eigenvalues of A, okay. So then the roots of chi A is, yeah, and the roots of ds have some connection certainly. In fact, it appears at the present moment that they must be one and the same. And indeed, in most cases you will find that the roots of ds and the roots of chi A turn out to be the same. However, there are some special cases when that does not happen. So in general, we will make this claim that roots of ds, yeah, they are a subset of the roots of chi A's. And why should it be so? Why shouldn't they be the one and the same? So if I have a set which is basically nothing but the roots of ds, and another set which is nothing but the roots of the characteristic polynomial, yeah, it feels like at this point that there is a connection between this ds and this characteristic polynomial. This is this chi A's, right? So why should they be, and then why should then this be a subset? Why not equality hold between these two sets? Well, that is because sometimes these C and B matrices have a tendency to be a little mischievous, yeah. Sometimes what might happen is, because of the structure or the entries in this B and C matrices, remember that C is a row vector of size n and B is a column vector of size n. It so happens, yeah, sometimes what happens is, because of this C and B matrix, you might have some cancellation. So there might be some factors that are common to ns. So remember, ns is basically the set of zeros, right? So we can factor them out like this, and ds is basically the set of poles, yeah. So the poles may be 1 to n and the zeros may be from I is equal to 1 to m, yeah. So there are m zeros and n poles. Now suppose this is the case and there are some pj's that are equal to some zi's, then there will be cancellation. However, when you are looking at the characteristic polynomial, you see if it is a 10 by 10 matrix, the characteristic polynomial has to be a monic polynomial, which means that the coefficient of s to the power 10 in the characteristic polynomial must be unity, and also the highest degree must be 10. So if it is an n cross n matrix, the characteristic polynomial must have a degree n, therefore it must have n roots, distinct or otherwise, yeah. It can be repeated roots also, but the total number of roots is 10. However, now you notice in the transfer function, if there is a pole 0 cancellation, then ds may or may not have all those 10 roots, right, or those n roots in the general case. Some of them might cancel out with the roots in ns. This will totally depend on what the entries in C and D are and what their structures are like which of the entries of C are 0, which of the entries are non-zero, which of the entries of B are 0, which are non-zero, what their numerical interplay is, right, how they interplay with this adjugate of Si minus A, everything will depend on that, right. So if this C and B together conspire in some ways with this adjugate Si minus A to have pole 0 cancellation, then sometimes you might have that not all eigenvalues of A, which are basically the roots of the characteristic polynomial, tend to show up as poles, right. So that is why these are basically the poles and these are basically the eigenvalues. So although we use the terms loosely speaking interchangeably, the poles and eigenvalues, in fact the controller design technique in state space domain is often called pole placement, right. But we must be a little careful while making this sweeping statement that this is nothing but a pole and things like that, right. So that is why we need to be a little cautious, yeah. Every eigenvalue may not be a pole of the transfer function, but every pole of the transfer function is definitely an eigenvalue of the A matrix. That is what we should we should do well to remember. Now of course this is a small brief digression once again, but that brings us back to our main point. What I am trying to now show is this similarity transformation leaves the characteristic polynomial invariant. So here is the claim. So this is basically in words. Mathematically speaking, suppose you have A, B, C, D and you have A tilde, B tilde, C tilde, D tilde for two different systems. So this is system 1, so rather SSR 1, okay, this is SSR 1 and this is SSR 2. So state space representation 1, state space representation 2. Yeah, the way to get from here to here is through that transformation matrix T, which basically, again let me write it, T inverse AT is equal to A tilde, T inverse B is equal to B tilde, C T is equal to C tilde, D is equal to D tilde. Yeah. So what I am claiming is that this characteristic polynomial of A is going to be equal to, so this is the claim, is it going to be equal to the characteristic polynomial of A tilde, okay. So let me start with the characteristic polynomial of A tilde first, right. So if I start with the characteristic polynomial of A tilde, what do I know it to be? Let me start with determinant of Si minus A tilde, which is further equal to determinant of Si minus, and A tilde can now be written as T inverse A T, right. Then I do this small little trick here, this identity I write as T inverse T. So I write this as T inverse T minus T inverse A T, the S is of course just a scalar, and then I pull out this T inverse from the left and T from the right. So here is what I do, I pull out this T inverse Si minus A, so remember this is basically chi A tilde S, yeah, I am starting with the characteristic polynomial of A tilde, and this is T, but then I note, and again this requires a bit of a proof, but of course you can look up that in any standard textbook, again undergraduate level maths textbooks would have it, that if you have two determinants, yeah, if you take the product of those two matrices and then take their determinants, it is the same as taking the individual determinants and then taking their products. The only difference is that this product is a different product from this product, because remember determinant is something that takes a matrix and spits out a scalar. So basically this multiplication is happening in the space of matrices. So you take two matrices, that dot here in the first line, so let me underline it with the blue here, this product here denotes that it is happening as the product of matrices, but here this product is basically the product of two scalars, okay. Again in words we say that the determinant of product of square matrices is the product of the determinants of the square matrices, right, but of course the products are not in the same sense. So then I go to the next slide and I see that this determinant of T inverse times determinant of Si minus A, this is further equal to and times determinant of T, yeah. Now once I am in the domain of scalars, I know that if I multiply three scalars then the order of multiplication is immaterial, yeah, and already sitting here is my chi A S, yeah. So this is further equal to, then I just swap this position here and push it in between. So I have determinant T inverse times determinant T times chi A S, but then again product of determinants is equal to determinant of the product. So I have determinant T inverse T times chi A S. Now this is of course the determinant of identity, but determinant of identity I know to be unity, yeah. So then this ends up as being chi A S. So therefore I have shown you that the characteristic polynomial is invariant under similarity transformation. That is a crucial detail, okay. It's a very important detail that the characteristic polynomial is invariant, okay, and therefore the poles and the eigenvalues are also invariant, but I have still not shown you that the transfer function is also going to be invariant under this similarity transformation. So let's quickly try and show you that. In fact we will be using the same trick again. So say GS is equal to C Si minus A inverse B, and G tilde S is equal to CT, I am replacing C tilde by CT, Si minus A tilde I am replacing by T inverse AT, yeah, inverse whole inverse times T inverse B, this is B tilde, right. So let me write that, this is C tilde, this is B tilde, and this is A tilde. So now I have to show that this, yeah, is equal to this. I have to establish this equality. If I establish this equality, then I would have actually substantiated the claim I made right at the beginning of today's lecture in this figure here, yeah, that eventually from all of these you end up going back to the same ODE or transfer function, yeah. So all these connections I would have at least justified in this picture, right. So how do I do that? Just let's take G tilde and be a little quick about it. So Ct, and again this I identity I can replace by T inverse T, and I take the T inverse out common on the left. So I have this T inverse out common on the left, then I have Si minus A, and then I have this T common from the right, yeah, and then this inverse, and then this T inverse B, right. Of course I can add the D as I like, it is the same thing here because D tilde is equal to D. So I will forget about the D, the crux of the matter is in showing that this part is equal to this part, yeah, the D will not play any role in this equality, it is by default equal. Now recall that if you take two matrices PQ and you take that inverse, then the order of the multiplication gets reversed and you get it as Q inverse P inverse. How to see this? Well, it is a very simple straightforward way to see this, just hit it. So you take PQ and Q inverse P inverse, yeah, take this product, so these two will pulverize and give you identity, so then you get is equal to P inverse is equal to identity. So now using the same concept here, we will take the inverse of this product. So this is one matrix, this is another matrix, this is another matrix, yeah. So we first take the inverse of this, so we get Ct, then we get T inverse, then we get Si minus A whole inverse, and then we get T inverse of T inverse. So double inverse, so of course Q inverse is going to be Q itself, right, by definition, yeah. So therefore we get again this T back here, yeah, T inverse is inverse of T inverse is T back, so then we have T inverse B. But what is this? Now if I open up the brackets, you see this T and T inverse will combine to give identity, this T and T inverse will also combine to give identity. So I will be left with C Si minus A inverse times B. Of course then this turns out it is equal to G. I started with G tilde and I got back G. So basically then I have shown you that GS is invariant under similarity transformation, yeah. So that is also another crucial and important bit, yeah. So we have seen that therefore not only are the poles and the characteristic polynomial invariant, also the whole transfer function is invariant. So the diagram that I had drawn there, I have shown you every single connection there, yeah, and that is why we call it a similarity transformation, hence it got its name similarity. Before we close this lecture, I would like to give you a short motivation behind why we went into this similarity transformation. Of course it is a topic that is interesting in its own right, because now you should go back and try to check and verify that indeed there is this relation between this change of basis, yeah. Basically instead of the standard basis we are now choosing the columns of this T matrix as our new basis, yeah, that is the basis transformation. For those of you who are a little more mathematically inclined, you might go and look up the linear algebraic implications of that. Now the point is that this should, because we are not doing this just for the sake of it, just because it is interesting, we have at the back of our mind this idea that we want to get to this e to the at without having to do those nasty Laplace inversions. Now what sort of a matrix is very easy or lends itself very easily to inverting? We know that it is a diagonal matrix, right, that allows us to invert very easily, because the inverse of a diagonal matrix is basically you take the reciprocal of each of the terms in the diagonal and you get its inverse, right, that is how easy it is. So suppose, wouldn't it be nice if there exists T such that T inverse At is equal to this lambda, which is, this is a capital lambda by the way, in Greek lambda, big lambda, which is basically a diagonal matrix. Why should that help us? Why is it good? Yeah. Now let us try to see this, why this is going to be beneficial to us, right? Why are we so interested in this such an existence of such a transformation or this diagonalizability. So okay, let me complete this sentence. If there exists T, then obtaining e to the at is easy. This is my claim, okay, and this is my motivation. So this clearly is a similarity transformation. So if there exists a similarity transformation that diagonalizes the original given matrix A, then it turns out that e to the at can also be evaluated with relative ease. That is my claim. So how do I establish this claim? So suppose you have this T inverse at is equal to this, right? Then you take for example Si minus A, sorry rather Si minus lambda inverse, yeah, that is going to be nothing but, so if you take the Laplace inverse of that, that is going to be nothing but e to the lambda t. But why is this easy? Because now you look at this, this is S, all these S's are sitting over here, that's Si for you, minus, then you have this lambda 1, lambda 2, I do not know, they could be same, they could be different. So lambda 1 could be equal or not equal to lambda 2, I do not care. Last you have lambda n, yeah, like this. And then this whole fellow's inverse I want to take, and then I want to take the Laplace inverse of that. So what is this? This is basically nothing but Laplace inverse of, just check, 1 by s minus lambda 1, 1 by s minus lambda 2, so until 1 by s minus lambda n. And this is very easy because now I know this is just going to be e to the lambda 1 t, e to the lambda 2 t, so until e to the lambda n t. That is it, right. So it turns out that for a diagonal matrix this is easy, but now given that I have this diagonal matrix, why should it make my job of finding, remember my goal is to obtain e to the at, not e to the lambda t. So even if e to the lambda t is easy, even if such a similarity transformation exists, what good is that to me? Here is how that helps. Once again, now observe that this, while this Laplace inverse of Si minus lambda whole inverse, on the one hand this is equal to this e to the lambda t like we have described in the previous slide, which is easy to get, yeah, suppose you have already got the diagonal form, then it is easy. On the other hand, this can be written as the Laplace inverse of Si minus, I believe it was T inverse At is how we represented this, yeah. Again we apply the same trick, it always works like that. So S T inverse T minus T inverse At whole inverse like this, yeah, whole inverse. So then again we pull out this Laplace inverse and we pull out this T inverse Si minus A and this T here, and this whole fellow's inverse we take, yeah, and then what we get is basically again we apply the inverse and in the reverse order. So first we get the T inverse pulled out from the left, I believe, yeah, the T inverse pulled out from the left, and then we have, okay, I can actually take it outside the Laplace inverse sign because this T is a constant. So I can pull out this T inverse and then this Laplace inverse Si minus A inverse and this T, which is nothing but T inverse e to the At T. So therefore I have this equality. On the one hand it is very easy to evaluate the exponential of a diagonal matrix. So suppose I have been able to diagonalize this through a similarity transformation, I can easily readily evaluate this e to the lambda t, and then I say that e to the lambda t is equal to T inverse e to the At T, which then leads me to conclude that if I want to get e to the At, I can just hit this, both of them on the left hand side by T and on the right hand side by T inverse because T is invertible, then I get e to the lambda T, T inverse, right. So this gives me a very nice handle. So in the next lecture we shall see what this entails, what this actually implies, this diagonalizability, when we can and when we cannot diagonalize this, and if we can diagonalize this, as we can already see here, yeah, this similarity transformation that allows us to diagonalize this matrix A into this matrix lambda is something that we love, because it makes the job of evaluating this this e to the at way more straightforward and kind of independent of this Laplace inversion. You might argue that we have taken the Laplace inverse at some stage, but you know, that is very trivial. Laplace inverse of s minus 1 by s minus lambda is not very difficult, yeah. So we will see more of this in the next lecture.